Trigonometric identity. Let me first state that chapter 8. Anybody remember the title of chapter 8? Analytic trigonometry, I think. Right? Just focus on the trigonometry itself, not motion, not geometry. The trigonometric function itself, and what can we do? Here is a fundamental identity. Let me rewrite this one. So we switched from t to x because we don't care about t now. Just the sign, no matter what that input is, we're going to call x. That meaning the sine squared x, it really means sine x whole quantity is squared. Right? They just type it simply like that. But you understand it like this. And cosine x whole quantity squared is equal to 1. Does it look like an equation? It is an equation, but it's a very special equation. The solution to this equation is all real numbers. Do you know any equation like that? You write down an equation, solution to that equation is all real numbers. Very silly equation like this. X plus 1 is x plus 2 minus 1. And you are sufficiently trained to see that, this is always equal to each other. Because very simple algebra, everybody sees it directly. That's the same thing. But if you view this as an equation, then no matter what x you plug in, it's going to be the same. And you clearly see that, right? That's like this here. And whenever that happens, we call it an identity. Equation is true for all real numbers, and it's called identity. And they're claiming this is not an equation, it's an identity. If you plug in x and x here, they're always going to be equal to 1. You can try going in sine of 70 squared, cosine 70. Use a calculator, it says 1. If you use 64 degrees, it says 1. Always 1, right? And mathematically, we're guaranteeing that it's actually always 1, no matter who does it or not does it, right? So let's see. We've seen this equation before. Something squared plus something equals 1. Where have you seen this? Since we're using this x, little x, let me use a capital X and capital Y. Then you might recognize it. Capital X recognize the first quantity, capital Y recognize the second quantity. Where did that come from? Equation of the circle, you know x coordinate is actually backward. X coordinate is cosine x, right? Y coordinate is sine x. If the angle is a little x radian, and the coordinates on the unit circle is capital X and capital Y. So it's almost a proof, right? And we proved it in this way. So I'm going to take this equation, this identity, and actually prove it this time. I mentioned about how this one proof of this one goes, but we're going to prove it here. Is that right? All right. This, we see why this is true. This is not like this. It's very different flavor, right? There's some algebra. This one is like more of a Pythagorean distance formula algebra. Okay? So this is a fundamental fact, and with all the identity you rely on. Exercise in this section 8.1 introduces 70 more identities. And they're a book of trigonometric identities. Nobody knows all these things. And if I put a new identity in the test problem, it's very difficult to do that in a short period of time. So we're going to go through like a typical problem, 6th problem here they introduce, and only assign very similar problem. So if you master those, you're going to be good with the test. It's going to be all just like that. All right? But understanding, well, kind of see the value of this thing is important. So what you're going to see is that it's not as obvious like this. They look very different, but by just juggling with this identity, it turns out it's a lot simpler or equal to the completely different looking. And it gets harder to recognize that. So that's why in mathematics, and you will see in the calculus and on, they do some more things to identify these two things are equal and different, not just relying on how they appear in terms of formula. Formula look different, but maybe input and output is exactly the same. So here is the first example. All the example in this section, 8.1 looks like this. Prove tangent squared x plus 1 equals secant squared x, period. We're going to prove this one. Is this an equation? Is a better term for that is an identity. So we're going to prove this identity. So either Weber sign explains this way, or you might have learned this one in high school. You're proving this way. Many students use the following. You take that equation and manipulate until you get 0 equals 0. And then you claim it's proved. It is an acceptable method. We can accept that. But my point of going through all these courses and then here is, of course, trigonometry is a useful thing, but logic is the most important merit of forcing, it's not a good term, to mathematics education to everybody. And this is a wonderful subject that you learn logic in a very rigorous way. So here's the thing. If you manipulate this, logic is like this. You assume this is true. And on top of that truth that is assumed, and you deduce another statement that is true. So that is of course valid as long as this is true. So logically it requires more explanation. So I'm going to do a slightly different method. It's logically more complete. Okay, so what I'm not going to do is take that equation itself and manipulating, because in that case everything is being based on top of that, assuming this is true, whatever you conclude from here. So here's how the actual better proof goes. We want to show this thing is true. You analyze it. It means the left-hand side is equal to the right-hand side no matter what x value you plug in. That's the meaning of this one, right? And that's what we're proving. So you separate left-hand side, LHS. What is it? Tangent squared x plus 1. Don't deal with the secant squared. Just separate that and try to rewrite and simplify it as much as you can. And then do the same thing to the right hand side and separately, and try to simplify it as much as you can. Maybe you're going to end up at exactly the same, and then conclude these two things are the same. That's logically better. So I ask you to do it this way. All right. This is our usual strategy. Simplify left-hand side, simplify right-hand side, and show these two things are equal to each other. Right. So this is the left-hand side. Peeking at the right-hand side, and just to get the direction, you can just do crazy things here. And nothing's wrong. It's just incorrect direction. So what is secant? 1 over cosine? Right? So decide to, maybe we should write this one in terms of sine and cosine. You've got to have a direction, right? There's different ways to do it. So how do you write tangent? So let me write it like the tangent x squared equals 1 plus 1, right? That's what that means notationally. Now I want to change the tangent. Go back to unicircle in terms of capital X and capital Y. Who remembers tangent x radian? Y divided by x, right? You don't have to do this anymore once you remember how this tangent looks like. But what is y in terms of trigonometry? Y coordinate on the unicircle is a sine of what radian? Y radian? X radian. This x is fixed, right? This is a little x, angle. You should look at it as if it's t. What about x down there? Capital X? It's a cosine x radian. Remember those? And that's squared plus 1. So I wrote tangent squared x plus 1 in terms of sine and cosine. Alright? You can distribute the exponent over division or multiplication. But you cannot distribute the exponent over addition or subtraction, right? So let's do that. What is the left-hand side? It's a sine x squared and cosine x squared plus 1, right? But now let's use this abbreviation, putting the square like that. It means whole sine x squared and cosine x squared. Is that okay? So we kind of broke that apart and got rid of some of the parentheses like that. What is the next direction? One thing is putting in the common denominator. Right? So this has a denominator, it does not have a denominator. So let me write that in here. Sine squared x, cosine squared x. So what are you going to do to about a 1 there to put into common denominator? Denominator? Cosine squared x. Numerator? Cosine squared x, right? So that it is 1. So put into common denominator, and then we can just write it like this. Think about how 1/5 and 3/5 add together. So 4/5, you add the numerator. Is that okay? Right. Well, at first, if you're trying this one for the first time, these things that I'm doing is not that immediate. Maybe you fail and come back in here to a certain stage and try different things, and hopefully going through the several examples, you get this idea that he's always using these Pythagorean identities. So maybe that's a goal. Try to pull out that shape, sine squared plus cosine x squared. You already see that it's here, right? So what is it? 1. That whole thing, sine squared plus cosine squared, is always 1, right? What is it called? Well, the first fundamental Pythagorean identity we just explained why it's true. So it's a cosine squared x. Well, that's simple enough. Suppose you didn't notice that this is actually secant squared, right? Many of your problems, hey, that's already secant squared, because 1 over cosine is secant, right? But sometimes it's not that immediate. Suppose you didn't notice that, and you end up here and you feel like, oh, that's simple enough. That's what I'm going to get to. Now you look at the right-hand side. Right-hand side is the secant squared x. And try to simplify. Well, to me, that's simple enough. If it is not equal to the right-hand side immediately, try to change it in a simple way. So, and then you think about, all right, this is secant x squared, and that's 1 over cosine x squared, and of course is 1 divided by cosine squared x. Alright? You try to simplify or rewrite each side, left-hand side and right-hand side, as much as you can, and hoping that at the end these two things works out the same. So last thing you have to state whenever you are asked to verify that is that not just separate the calculator, correctly concluded. The whole purpose of these two calculations is to acknowledge or verify or establish this statement. No matter what your x is, left-hand side and right-hand side initially look different. Now it looks exactly the same. Therefore, it's equal to each other. This is how I want you to prove identities in this section. All right? So the main tool in this proving is simplifying and rewriting this expression using the basic algebra that might require common denominator method, plus one more. What was it? That very first fundamental Pythagorean identity. All right? If you haven't used the Pythagorean identity anywhere in the test, for example, you probably did something wrong. So make sure you use that identity somewhere to prove this problem. Alright, so that's what we're going to be doing. So the first task is working on some simplifying expression exercise. Instruction of this type of a problem, simplify expression, is kind of very vague. To me, that looks simple enough, and why would you mess with that? So I'm just going to give you a clear instruction in here, and we're just merely just using it as a tool to actually establish an identity, so it's not going to be vague in that way. So write everything in terms of sine and cosine. Right now there's a tangent there, right? Try to simplify as simple as it is possible in terms of sine and cosine. Get rid of that tangent. That's further instruction I'm giving you in here. So let me make this one exercise. So exercise here, simplify this expression you see in terms of sine and cosine. Maybe it's just in terms of sine. Maybe it's only in terms of cosine, right? Try to simplify it as much as you can. I hope many of you got to this point. Cosine t plus sine squared divided by cosine t. Fair enough? Yeah. Now, this stage you might try to combine into common denominator. And let's think about what could be the common denominator. There's no common denominator here, so you will put that common denominator to be cosine t there, right? And if you put cosine t, what's the numerator? Right. It's a cosine t whole quantity squared, but it's going to be abbreviated like this. Right? When you put it squared later, you must put parentheses. But they usually write like this. Is that okay? Yeah. Now you have a common denominator, and you can do further simplify. So once you put it like this, there is a cosine squared sine squared again. That's Pythagorean identity 1. And 1 over cosine t can be further simplified to secant t. Right? That part is unclear. That's unclear. When I said it's sine and cosine, so that should be the answer if that's the instruction. Shouldn't enter a secant, right? But it looks like even simpler, so I changed my mind. Is hey, that looks simpler, and I changed it. So it's very unclear instruction. I hope you good luck with WebAssign, whatever they want to try to simplify it. But I hope it's not going to be like this in the test. It's going to be all proving the identity. So you use this to prove this identity. All right. So there's one more simplifying expression. It's the following. All right. What's different about this one? Two denominators look different, right? So in general, let's think about how we're going to do this. If a and b are not numbers, some expression like this, and there's a c and d, like this, how do you put it into common denominator? Let's think about that. First, the b, what could be the good common denominator? Without knowing how the b and d actually looks like. Just combine it. What? So b, so what is it? B times d, you see that? If you do b times d, there'll be nice there. By multiplying d, and that first term has the denominator bd, multiplying, what do we multiply the second one? B in there. Then we're going to have the same denominator, right? And originally we have a c up there, but we're inserting b there, so you have to go b up there like that. If two denominators are different, you can always do that. It's sometimes overdoing it. Right way to do it is the least common multiple, but we don't know how the b and d looks like, so this is a multiple, not necessarily least common multiple. It still does the job. So this makes sense? Then we can put it together to common denominator BD, AD plus BC. So that's how you put it together in general. That gives you a clear idea. Some people just don't like this and are very good at memorizing stuff. And then you can just do it like this. All right, whenever I see this thing, I'm going to do this. I'm going to multiply these two denominators, put it down there, and cross multiply and put it up there. D is multiplied to A, B is multiplied to C. And you get here quickly. If that feels like another thing to memorize, you don't like it, and understand the procedure, and arrive to the correct one way of combining two fractions. Is that okay? All right. So there it is. This is like A divided by B plus C divided by D, right? So the first thing is the exercise is that use this idea to put this thing into, put it into a common denominator form, right? And combine them. And then we're going to further simplify together. But this part is right now exercise. How was it? Is that all right? Okay, so I'm showing it in red color here and what to multiply numerator and denominator to put into common denominator here. And then I just put them together. All right, have we used Pythagorean identity yet? It's just a simple algebra, right? So do you see where it's coming in? There's cosine squared. So if you have sine squared, that would be great, correct? So let's do that here. So you kind of expand this. There's a sine theta plus sine square theta. You see that? And there was cosine square theta out there. And we have a denominator there. All right. Okay. What do you see now? This one is just going to be 1 because of the Pythagorean identity. Sine theta plus that whole thing is a 1 and the denominator there. Okay. So we can do more. Just let me know what you see here. What do you see? Yeah, 1 plus sine theta looks a lot like what's in the numerator, right? Just in opposite orders, 1 plus sine theta. So we cancel those. What happened if you multiplicatively cancel these things? What happened to the numerator? What remains there? 1. Make sure you get that. It's cosine theta. Right? So let's further simplify this one. What is it? Secant theta. All right. Look at here. This thing is just simply secant theta, right? No matter what you plug in the left hand, this expression is going to be equal to that secant theta. So it's very different from well, it uses polynomial algebra, but additionally there's this trigonometric Pythagorean identity that changes the shape a little bit. All right, so we're going to be doing this to prove identities in there. So this is our first identity problem that you're going to be doing on your own. So here is problem example 3. Let me see if that's going to be sufficient space here. Guess not. All right. First, I want you to write down this expression. Not expression, just an equation. Not an equation, it's an identity, it's supposed to be. Cosine theta times the secant theta minus cosine theta, close parentheses, is equal to sine squared theta. We're about to bring that. Actually, statement A says verify algebraically that equation is an identity. That is what we've been doing. I'm just going to explain part B and not doing it. So part B is saying confirm graphically the equation is an identity. Graph of a function takes this much of information. Theta, you choose some value of theta, and here's y value. Let's say that was left-hand side function. And you plug it in there and get some value in it here, right? So this one doesn't show you how you calculated input and output. It only shows you what your input theta value is and what your output y value is. This graph only records that. And that's what this statement is exactly is. The value in the left-hand side, which is this value here, is the same as the value in the right-hand side. Maybe it's going to be z here. So if you collect them all that for given the same theta value, what you get for the left-hand side is supposed to be exactly what you get in the right-hand side if these values are always equal to each other. So if you sketch the left-hand side function and right-hand side function separately using the calculator, you're supposed to see that the shape is exactly the same. To our eyes, it appears to be exactly the same. That is not a proof, but it is one way to verify. Okay? So that's part B. We're not going to do part B, just part A. That's your exercise. Right, was that okay? And here's one thing I'd like to say at this stage is that you are asked to kind of explain this thing is true, and at the end you shouldn't have a tendency that I don't know, this and that is supposed to be true, so I'm just going to write down whatever it's supposed to be, right? So don't skip calculation. This is about not getting an answer, is you thoroughly explaining why left-hand side is equal to the right-hand side. And at the end, don't jump to the calculation, I don't know, it's supposed to be that, and then you just go to that. Of course it's true, but it's not thoroughly explained. That's not verifying, right? If you're discovering this one, and then you briefly like this, then I will believe that you knew what you're doing. But I already gave you the answer. These two things are the same, and you can just pretend, you're explaining this, but that's not what you're supposed to be doing. So do not skip calculation. Thoroughly explain why these two things are the same. Okay? All right, let's try next one. How do I skip this one? How do I dunk it easily? Just whispering to myself. So this is your exercise. Okay. Did everybody kind of come up to here and got 2 times the sine x in the numerator? That's a good sign. Then left-hand side have 2 times the sine x in the numerator, right? The denominator looks different. Well, I'm just going to claim that that's equal to cosine squared, and that's the part that I'm going to be unhappy about if you just set this one into 2 sine x divided by cosine x, right? You have to explain a little bit more there. So what happened? What do we do? You multiply this out, right? Which is in the form of a minus b, a plus b. Remember that? What happened if you multiply a minus to a plus b? Is a squared minus b squared, right? Or you can multiply out. And you will see that is that 1 squared, which is 1, minus sine x squared. That doesn't affect negative, it's just that. Alright. Then you've seen 1 minus sine squared before, right? Let's see. The goal is that you're turning this one into cosine squared x. And of course that is coming from Pythagorean identity like this. Here's 1 minus sine squared. So you can see cosine x squared is 1 minus sine squared. Right? That's how you explain things that why that becomes cosine squared. It's 2 sine x divided by cosine squared x. What is it? One last thing you do? That factor, you acknowledge the left-hand side you calculated before, and right-hand side you calculated here. They are equal to each other. And that's why these two things are always equal to each other. Okay? That's it. We stop here.